Hello everyone. In this video, we are going to solve some problems on basis of the derivations that we did in the previous video regarding the shear energy balance for a rectangular film. So first of all, problem you can see that this is the first problem that we have. It is about the heat loss on the rectangular film. This problem we have taken. It is from the BSL book, problem 10.8.2. So you can refer there also. So first of all, we'll see what data we have been given. We have been given the ambient and air temperature, then the temperature of the wall, then the thermal conductivity is given to us, and the dimensions of the fin is given to us. So we have been provided with this sort of data, and what we have to do is we have to find the heat transfer that could be taken from this fin under the steady state conditions. So all the units that we have been given, they are in Fahrenheit and feet and inches. So we are not going to mess up with the units. We are going to keep them as they are. So you can try to solve this question on yourself. I'd be solving it in within 2 to 3 seconds. You can pause the screen and you can solve those questions. So let me move on to the solution. Uh, so first of all, what we're going to do is we are going to have unit consistency. We have been provided with the thickness in inches. So what we're going to do is we have to change this thickness into feet for the unit consistency. So according to this conversion, we are going to change our uh, thickness of fin in feet. It comes out to be 0.01333. So that's how we get our lambda value or the thickness value. Secondly, we'll find the theta naught value, which is defined as T wall minus T infinity. So we'll get our theta naught value as 150 degree Fahrenheit. So these are some necessary values we require to move further. So secondly, we'll find what is the cross sectional area and what is the perimeter of the fin. So cross sectional area is basically this area we are talking about. This is the cross sectional area of the fin, and perimeter of the fin that we have discussed over there is defined this perimeter. So red is the perimeter and green is the cross sectional area for our problem. So a cross sectional area is given as width into breadth, as you can see over here that how cross sectional area is given as width into breadth. This overall area is the cross sectional area. Secondly, we have perimeter. Perimeter is 2 times width plus breadth. So accordingly, we find those values as the 0.133 feet, 0.01333 feet square, and 2.0266 feet. These values we get from the given data. Secondly, it is important for us to find the fin parameter. So we'd use the standard equation that we used in earlier problems. In earlier problems to find the fin parameter, it is given as under root of HP upon KCS. So we'll put the values that we have over here: the value of H, the value of perimeter, the cross sectional area, and the thermal conductivity. These values are given to us in the problem. We put those values, we'll get the fin parameter value at 17.44 feet inverse. So what we are going to do is we are going to simply put those values in the equations that we have derived earlier. So this is the equation we are going to talk about. So our problem is it is basically concerned with the insulated tip. So the derivation we did earlier, it was for the long infinite fin, rectangular fin, which is long and infinite. But here we are going to use the formula that is correct for the insulated tip, where at the tip of the rectangular fin, no amount of heat transfer is taking place, which in reality, which sort of matches very much with the reality. So we are going to use this formula, and this formula we're going to use in upcoming problems also. This formula where this tan hyperbolic ML comes out to be extra. So we'll put the values that we have found in earlier slides into this equation to get the Qfin value of 2087.9 BTU per hour. So what we do is we individually find the dimensionless length value. We'll find the tan hyperbolic value, And the base term we are going to find, and we'll substitute these terms into this equation, and we'll get this final heat loss. So, as asked in the questions, we have found the heat that our fin is dissipating into atmosphere for the cooling purpose. Now we are going to move on a second problem. It is also regarding the rectangular film. In here, we have been provided with the necessary data that would be coming across to solve the problem. So what sub questions we have over here is we have to calculate the average heat transfer coefficient. So heat transfer coefficient value is not given to us. Thereafter, we have been given with various values of different parameter ml, dimensionless spin parameters such as ml, whose value varies from zero point 0.3 to zero point 0.6, 0.81368. So this is the first part of the question. And second part of the question, it sort of asks us how what sort of trend we are observing when we change the value of an parameter. So we are going to solve this question now. So we'll see the solution. First of all, we need to find the basic parameters that we come across while putting values in the final equation. So we need to find what is the value of theta naught. It is given was t wall minus t infinity. So we take these values and we substitute in this formula to get the theta naught value. We have been provided with the dimensions of the fin. We write those dimensions. Then we find the cross-sectional area of the fin and the perimeter of the fin as we did in the earlier question. So here we are not provided with, this is the important and crucial part of this question, that we are not provided with the value of heat transfer coefficient. So what we have to do is we have to use this analogy of ml. We are going to substitute the value of m. We are going to substitute the value of m as root of h p by k a. This is the value we are going to substitute. We're going to multiply both sides by L. By multiplying both sides by L, then we can find H as a function of my fin parameter. That's what we are going to do is we are going to find H as a function of fin parameter. So using this sort of approximation, we are going to have this relationship over here. Here what we are assuming that the width of the fin is much higher than the breadth of the fin. Thus our perimeter value reduces to 2W instead of 2W plus B, which is the in general value. Our B is too small. So what we're going to do is we're going to neglect this term and we're just going to write 2W. After doing this approximation, we reduce to this equation. So what we are going to do it, we in Tableau format, we are going to have this values like what value of dimensionless parameter, what corresponding value of h we are getting, and with respect to that corresponding value of h, what heat transfer rate we are expecting. Because our heat transfer rate involves the value of ml as well as h. So it is function of both ml and h. So what we are going to do with, we have the value of ml. With this value, we'll find the value of h, and using these two values, we are going to find the values of heat transfer q. So for various values, we have found the corresponding h values and the corresponding heat transfer rate. And as you can see that as we increase the value of dimensionless parameter ml, our h value correspondingly increases, while our heat transfer rate corresponding also increases. So what we can comment about the trend over here is that as the value of parameter ml increases, we see that the heat transfer rate is enhanced. The heat transfer rate is enhanced significantly, even for the slight change of the fin parameter ml. So we can see that for a slight changes that we are making in fin parameters, our heat transfer rate is increasing significantly. So it becomes sort of easy for us if we want to enhance the heat transfer rate significantly. We can do necessary modifications to adjust our dimensionless parameter ml. So this is the solution of our second problem. Now we would be moving on to our third problem. So this is the third problem that we are going to solve. In here also, accordingly, the two questions that we have solved earlier, the data is given as the length of the fin, width of the fin, and the thickness of the fin is provided. The necessary conditions are provided as a thermoconductivity and other necessary constants are provided. So what we have to do is we have to perform a shell heat balance to find the total amount of heat that is being transferred, then the temperature at the tip of the fin. So this first part we are not going to go into much deeper because it is going to be same as the above two questions. We have to simply substitute the values. Will find the value of theta naught and will substitute this values of area and perimeter to get the fin parameter, and accordingly we put these values in this formula that we have used in earlier questions to get the heat transfer rate. We will not go into that. But for the second part, what we have to find is we have to find the temperature at the tip of the fin. So, in case this is the different part from the prior two questions. So, what happens in this question? We are considering a insulated tip. So, we can't directly comment or directly use the formula that we derived earlier uh, for the what we formula that we derived for the infinitely long fill. We can't use that. So, this is the formula we are going to use for the for given specific problem. So for the insulated tip, the dependence of temperature on location x is given by this relation where it is the hyperbolic function of cosine. So what we are going to do is we are going to put boundary condition over here. At x is equal to L, we are going to put value of 0 L in terms of L, and the value of cos hyperbolic 0 is given as m. It is given as 1. This numerator term reduces to 1. So our theta at L can be written as theta naught, this term, divided by cos hyperbolic ml. So cos hyperbolic ml, we can find this ml value from the fin parameter and the length that we are considering for our problem. So we'll substitute ml values to get theta L value at L. To get this, we get this value as 54.2 degrees Celsius. But as we have seen, theta is just defined as temperature at x minus temperature, uh, the temperature ambient. This is how we define theta. So we'll substitute this value over here. So we have got the theta value and we have got the T infinity value. Correspondingly, we can find T infinity value. So this term goes over there, and my Tx value can be found by adding the ambient air temperature with the value of theta. Thus, we get 74.2 degrees Celsius as the temperature of the fin. So this is how we have solved our third question. Now we are going to move to our next question. This is the final problem that we are going to solve today. It is about the analysis of cylindrical spine. So in this problem, we don't have this sort of fin. Instead, we are having the cylindrical fins instead of this place. So our fin is sort of like going to be like this dimension. This is often this is how often is going to look like. So what we have been provided with is the value of the thermal conductivity. We have been given the diameter of the fin and the length of the fin. We have been provided that it is an insulated end, and the ambient air temperature is 60 degrees Celsius, while the heat transfer coefficient is 55, and the wall temperature is 95 degrees Celsius. So we have to find the fin efficiency, the temperature at the end of the fin, and the heat dissipation that is taking place from the fin. This particular problem I've taken is from R.K. Rajput heat transfer and mass transfer. So you can refer there for more information. So we are going to solve this question now. So first of all, what we're going to do is we are going to define what parameters we have. So we have diameter of the fin, we have length of the fin. This is all the given data. From given data, we'll find the theta naught as we did in the earlier questions. So then we are going to find the fin parameter, the most important parameter while consideration. So we'll use the standard formula. The standard formula is valid for the case of cylinder as we have derived for the case of uh, Cartesian system. It is also valid for our cylindrical system. So for cylinder, as we know, that perimeter is given as the uh, circumference of the circle at one corner of that cylinder. So our pi d is the perimeter for our cylinder, while pi d square by 4 is the cross sectional area of our cylinder. So it this perimeter by area of the cross section term, it is reduced to 4 by d term. What we can do is we can directly substitute this term over here in place of p by a. So this overall term is reduced to 4h upon kd and will substitute the necessary values that we have been given in problem. Thus we get the fin parameter as 23.936 meter inverse. Then if we have to find the dimensionless ML, which we'll be using in further formulas, which simply multiply the fin parameter with the characteristic length that is provided to us in our data. That's how we are going to get our ML value. So we have been asked with the fin efficiency. So as we have derived earlier, our fin efficiency is given as the tan hyperbolic dimensionless length divided by the dimensionless length. So substituting simply the formula, we get the 62.2% fin efficiency for our particular given data of the fin. So thirdly, we have to find, so this is how we have found the fin efficiency. Then we have to find what would be the temperature at the edge of the fin. So as we did in the prior question, we used this formula of heat cos hyperbolic formula. So we are going to use the same formula for the insulated fin case. So if we are going to just substitute values that we did in earlier case at theta L, that means at x is equal to L, we are going to have this theta value. This is the standard temperature difference with respect to ambient temperature. We are getting it as 15.81 degrees Celsius. So that means that our fin is basically 15.81 degrees Celsius hotter than the ambient air temperature. But what we're going to do is we are going to use the definition of theta that we defined earlier, and substituting those values, we get that the actual tip temperature comes out to be 75.81 degrees Celsius. Now we are going to find the total heat that is being dissipated by the fin. For this thing, we are going to take leverage of the efficiency of the fin, that the formula that we have derived earlier. We found that 62% effectiveness of fin is offering to us. So using that information, we are going to leverage what amount of heat of fin is sort of emitting. So what we'll do is we'll take the maximum uh, energy of fit fin that can emit on the basis of the theta naught. So we assume that the overall fin is acting such that the temperature difference is constant and is at theta naught. Theta naught is basically the T wall minus T ambient as we have defined earlier, and H is our heat transfer coefficient that is given in the problem, and AS is the surface area that is available for the heat transfer. So that's how we take the value of Qmax and we put that Qmax value over here. And this is the effectiveness of the fin that we have found over here. So substituting those values, we get the value of um, energy or heat that is being emitted by fin as 2.709 watt. So that is how we have solved this question to get the heat dissipation of the fin, the temperature at the end of the fin, and the efficiency of the fin. So that's how we solve this problem. So in all the four problems, we saw that how to find the heat emitted by a fin, how to find the temperature at the end of the insulated fin, or how to find the effectiveness or efficiency of the fin. So that's with that, I would like to conclude for this video. We have solved all those four problems that were necessary to get the crux of what we did in the earlier video regarding the derivations of the effectiveness parameters and the heat transfer parameters. Thank you.